You have two ways of seeing the potential produced by a point charge. The first way is to look at in this way, as we have done. This is the, well, not possible, any charge could be positive, negative. The charge Q, you bring the charge Q naught, you bring it here, Q naught from the infinity, and you say that there is a potential energy, E sub P, that is K, Q, Q naught, divided by the distance R that separate the distance R that separates. So this potential energy is E sub P of R. You define the potential V of R like the potential energy per unit of charge. So you will have that the potential produced by the charge capital Q by the source will be KQ divided by the magnitude of the distance R. So this is the potential at this point, V of R. I want to show you that if you do the same thing with our equation, with a definition, ddV is minus E ddr. Okay, ddr. Let's go to do it in E scalar ddr. Let's go to do it in one dimension maybe, or let's go, no need. Okay, minus E, so ddV will be minus E will be minus the electrical field, the K, Q, the Q divided by R. The electrical field will have the vector direction unitary vector R scalar ddr, and the vector R scalar ddr, this we have said that is ddr, so ddV is minus KQ divided by R ddr, sorry, R squared. This is the electrical field, R squared. So what will be V? Well, we integrate from 2 points. Let's say that we integrate from point V1 to point V2. So we will write the equation like this. We will choose the initial point V0, like V0. We will assign the value of V0 when the radius is R equal to R0. And we will assign the potential V when the radius is R, this R. Okay, this integral, if you make it, will be KQ by the integral minus sine 1 R squared ddr. But the integral of minus 1 R squared ddr is this value. So V minus V0 equal KQ multiply by 1 over R minus 1 over R0. So this is the potential. The potential V will be V0 plus KQ 1 over R minus 1 over R0. So now I want V of R. V of R will be V of 0. I will choose V of 0 to be 0 when R0 is the infinity. So this is my point. In R0 infinity, the potential V0, the value is 0. So it's 0 plus KQ divided by R. And again, because this quantity, 1 over the infinity, will go to 0, so this is the potential again produced by a point charge. So 2 ways to find the same value. V of R equal KQ divided by R. So wherever you see a point charge, positive, another negative charge, at the point P, they produce this charge that is at distance R1 will produce V of the positive charge will be K, let's say Q1, Q2. At the point P, the potential at the point P will be the potential produced by the charge 1 plus the potential produced by the charge 2. The potential at the point P will be K Q1 divided by R1 plus k q2 divided by r2. So r2 will be this distance, the distance from the source, from the charge. So this is the potential produced at this point of this configuration. And we will practice this idea with one example on the next video. For example, just to remember, we did in class this problem that is an interesting problem. We have a positive charge, the proton. At this point P, the proton at this point P, the particle, the proton, will produce a potential at the point P, and the potential will be K, the charge of the proton divided by R, the distance divided by R. So let's say now that I put an electron here. If I put an electron here, now if I put the potential energy U of the system of the 2-point charge will be the charge of the electron by the potential at the point P. So this will be K Q positive, Q negative divided by the distance R. And this is the atom, this is the potential energy of the atom. This potential energy is a negative potential because positive by negative will give a negative sign, and this is the potential energy of the system. So knowing the potential at the point P, whatever you plug in the point P, the potential energy will be the Q that you plug in the point P by the potential at the point P.